Demo is going to be about simple and simultaneous regression. I'll be running a couple of very simple examples, and we will talk about the output and what does it tell us. So this is the same example we discussed in the lab. So we are trying to predict frequency of substance use at the age of 16 using some IVs, using some variables at the age of 10. So we have affective disinhibition, cognitive disinhibition, and behavioral disinhibition measured at age 10, and then we are trying to figure out if we are able to predict frequency of substance use at the age of 16. To just start off with a very simple example, I'm interested in whether affective disinhibition is predicting frequency at the age of 10, and if yes, to what extent. So to run that analysis, I am going to go to Analyze. Now, you need to remember that when you're talking about regression, especially in these examples today, all of our variables are continuous. So let me go back to that again. So we'll go to Analyze, we'll go to Regression, and we'll go to Linear. Once we get to that, we are adding our dependent variable independent box and our IV that we want to test in the independent variable box. At this point, we're just running simple regression, so we're just looking at one variable predicting our dependent variable. So everything else on this part stays the same. Make sure that this method is enter. In statistics, we are defining our confidence interval at the level of 95%, and then we are interested in descriptive statistics, and this is it. For plots, you can look at the plots for residuals, and this basically would give you an idea of if there are outliers in the data. And again, we're not getting into what to do if there are outliers. That is something that we will discuss in the lecture. And then, you know, the how would you actually deal with something like that. So anyway, so we're running the plot with a histogram plot with dependent variable and the z residuals. We continue that. You can also save the predicted value and residuals. If you click on that, this is going to create additional variables, and that will basically give you the unstandardized predicted value and residual value for each of the cases. And again, this is helpful if you are trying to figure out outliers in your data and stuff like that. So I'm just going to run it. This is not necessary for our lab, but again, I want to tell you where those options are in case if you want to run those in the future. We'll hit continue. We are not touching anything else, and we are going to hit OK. Now, before we talk about these tables, we want to look at our data now. So you see that it is giving us the unstandardized predicted and residual values here, and you can explore further into it and see if there are any data points that are going beyond, way beyond the range of the other data points. So that is additional analysis we're not getting into. All right, so let's look at the tables that SPSS is giving us. So basically, the top one is our descriptive statistics, mean standard deviation. Then we have correlation between the variables. Then there are tables. This table basically tells us what variables we entered in the model, what kind of method we used. This one is basically giving us the most important statistic that here for us is the R-square value, which basically is telling us how much of the variance is explained by our independent variable. How much variance in our dependent variable is explained by our independent variable, which is 0.158. We typically convert this into a percentage, and we would say 16% of the variance is explained by our IV here. So yeah, so you would report that. ANOVA table gives you F statistics for the overall model, basically telling you whether the model was significant or not. In this case, since we have only one IV, we are more interested in the values from this table. And this table is giving us the value for regression equation. So this constant under standardized coefficient is our intercept. Basically, it tells you when our independent variable is 0, what would be the value of y. So kind of like where the plot is starting, or the intercept of that. And then this is giving us the weight for each of the independent variables in the model, and you can use this. You can use this to write a regression equation and then insert values in it to get points for your plot. So we'll talk about that in future labs about it, but basically this is where you are looking for the regression equation values. Now, important thing to consider here is that you have two kinds of coefficients given. So we have unstandardized coefficients and we also have standardized coefficients. Now, you typically don't report both. You report either of these based on what kind of data you have, what is your question, and what are you trying to answer. Basically, you're using unstandardized coefficients when you have meaningful units. So, it doesn't make sense to convert them into the standard deviations. So basically, for example, if you're talking about time, you're talking about days, measurement, something that does make sense. So for example, here, our dB is actually frequency of substitutes at 16. I think it's in days. So it might make more sense to actually report our B's or unstandardized coefficients and betas. Now, with a value 2.630 basically means that with 1 unit increase in affective inhibition at age 10, increase the frequency of substitutes at 16 by 2.63 days. For beta, which is our standardized coefficient, value 0.397, if you rounded, it becomes 0.40. Basically, this tells us that 1 standard deviation increase in affective disinhibition at 10 increases the frequency distribution by 0.40 standard deviations. These values can be positive, these values can be negative. When we have negative values, then you are talking about a decrease rather than an increase. And then we have t-values and significance related to that. So this is something that you would be reporting as well. And then if you are reporting the unstandardized coefficients, you would also be reporting the confidence interval. If you're reporting beta, then you don't have to worry about it. Another thing is to just be mindful of how the values in this table are related to each other. So for example, if I were to calculate the t, if I have a value of standardized coefficient and standard error, I can just divide those two values. So 2.630 divided by 0.401 would actually give me a value of t. Similarly, I can calculate beta value using B value and the standard deviation values up top here, and then you can refer to your book for details in terms of exact formula. But then you can pretty much, if you have either beta value or B value, you can get values for each one of those. And same goes for the confidence interval, because you have confidence interval for unstandardized, you can use those values to actually get confidence interval for beta. Again, you would use the same formula, but you would have to calculate each one separately. And again, you can refer to the book to get that information. And you all already are familiar with how this table relates to how the values in this table relate to each other. So if you need to review those, you can look back into your homeworks from previous labs. Basically, this is all you are reporting for simple regression, and then we also plotted additional charts to look at how normally distributed your data is, also looking at whether there's a linear trend, and there are additional things you do, there are additional charts you can plot to look at specifically at the skewness and linear trend, and that is something that Kate is going to talk about in the lecture when she covers the assumptions and diagnostics for regression. So I'm not going to get into that, and if you have additional questions, we can talk about that in class. So this is one of the examples for the simple regression. Let's get into an example for a simultaneous regression or multiple regression. So let's go to, so for example, we want to test whether affective disinhibition still predicts frequency even after frequency of substance use, even after we control for cognitive disinhibition, for example. So to do that, we will have to actually go to the same options, but this time around what we're doing is we're also including cognitive disinhibition in our model. So just one thing to remember about simultaneous regression is that we are adding all of the variables that we are interested in the model at the same time. That's why it's called simultaneous regression. And then when we interpret the results, basically what we're doing is we are controlling for the other variable in the model. So we're controlling for other independent variables. So basically in this example, when we want to make sure that even after we control for cognitive disinhibition, we want to make sure that affective disinhibition still has an impact on the frequency of substance use. So we are doing this. Everything else remains the same. You can, I'm not going to save these values, but you could, what this does is create additional ones. And since there are more variables in the model now, these will be different than what we had before. So you can do that, but it's not necessary again. And then we'll hit OK. So this time around, it gave us kind of like similar idea, the same kind of tables, but we'll have additional, obviously, values in it. Starting off with same descriptive statistics, we also have correlation table. We look at the R-square value. So this time around, it's actually 18% of the variance that it's explained by both of these IVs in our model. So overall, this model is explaining about 18% of the variance in the model. We look at the ANOVA. Overall, the model is significant again. And if you look at the coefficients, we see that when we're reading affective disinhibition, so basically this is the controlling for cognitive disinhibition, we still see that this comes out to be significant. And then we also see that we can also interpret the results the same way that we have done in the past. Cognitive disinhibition line, we would talk about that in the same terms. So controlling for affective disinhibition, 1 unit increase in cognitive disinhibition would actually decrease the frequency of substance use at 16. So these values are actually in negative. So you would talk about a decrease rather than an increase. And then so you would talk about each one of those. And basically this is how you would report your multiple simultaneous regression. The only thing is when you do have something like that that has more than one IVs, you want to have a summary at the end once you talk about all the statistics. I think this is pretty much it. We have looked at how to run a simple regression with one IV in our model, and then we have also looked at how to actually look at how to run analysis for a simultaneous regression. So hope this is helpful. Please let me know if you have questions. Thank you.